Now that we understand an augmented matrix, let's take a look at row operations, which will lead us to Gaussian and Gauss-Jordan elimination. One way that we can solve a system, again, is using an augmented matrix, like we have here, and elementary row operations. So row operations essentially can be three things. I can either switch two rows, which can be helpful, and basically I would just flip-flop them. So I want you to notice a couple of things. Here's my original augmented matrix. This is the notation that shows me what the row operation is, and it's saying exchange row 1 with row 2. So then my resulting matrix would be that the 3, 1, negative 2 would be row 1, and my new row 2 would be 5, negative 2, 3. The next operation is I can multiply a row by a non-zero. I cannot ever divide, so if I have to divide by something, like say I have to divide by 5 instead, I will multiply times 1/5 because it does the same thing, but division is not a row operation. So here, if I'm multiplying a row, notice this tells me I'm taking 2 times row 1, and the result is my new row 1. So that's how we read this. This is the operation being done. The result is going to be placed in row 1, which means nothing at all happened to row 2 here. So I'm just going to copy it exactly as it was. The first row is now doubled, so I'm taking 2 times each of the values. So 2 times 5 is 10, and 2 times negative 2 is negative 4, and 2 times 3 is 6. I can also put together adding rows and multiplying rows. So this one, feel free to do as much side work on scratch paper as you need to, but again, notice I'm changing row 1 only, and so row 2, just as before, didn't change. So I'm just going to recopy row 2 so that I don't get confused and try to do something with it. My new row 1 is to take the existing row 1 plus 2 row 2's. So I just do the math in my head, but if you want to write out what 2 times row 2 is, this would be 6, 2, and negative 4. That would be 2 row 2. And then I'm adding 5 plus 6 to get 11, negative 2 plus 2 to get 0, and 3 plus negative 4 to get negative 1. So again, feel free to do this work on scratch paper. Don't show that work because it'll get confusing when you're trying to show me each row operation that you're doing. But feel free to sort of write that down to help you to know what 2 times row 2 is, or simply do it in your head. 5 plus 2 times 3 is 5 plus 6, which is 11. And you get the idea. So that's the 3 row operations that we will use. So I'm going to take you through 2 opposite examples for row operations. Before I do that, I want to give you sort of the big picture, or why we're doing this. Remember that this augmented matrix that we have written, that's where we're starting, is 2x plus 3y equals 6, and x minus y equals 8. And last week we did substitution or elimination to solve this, to find what x equaled and what y equaled. Well, this week we're going to use different ways using matrices, but specifically for augmented matrices, I want you to look at where I'm trying to end up here. And where I'm trying to end up is at 1, 0, and then there's going to be some number here, and 0, 1, and there's going to be some number here. So why do I want to end up there? Because the first line would be 1x plus 0y equals whatever number I come up with, and the next line would be 0x plus 1y equals whatever I come up with. So when I get done with all of these operations, I'm going to end up with the answers that would go in my ordered pair. So it's important for you to understand why we're doing what we're doing. So now let's take a look at how to do what we're doing. How we do it is essentially, I already have given you the row operations here, and I want you to fill in the new rows. So my first line, notice I recopied row 2 because row 2 didn't change. Notice the only one changing is row 1. to get my new row 1, I'm going to take half of the existing row 1. So that's half of 2 is 1, half of 3 is 3 halves, half of 6 is 3. So I took that original row 1 and took half of it. Now, notice the only one changing is row 2, so row 1 is just going to be recopied, 1, 3 halves, and 3. And yes, I could make 3 halves into 1.5. I'm going to leave it as a fraction, and you'll see why when I get down here. Row 2 is found by taking row 1, and when I say row 1 minus row 2, I'm talking about from the previous step. So I'm taking this step, and I'm taking row 1 minus row 2. So 1 minus 1 would be 0. 3 halves minus negative 1. Show all the work you need off to the side. Negative 1, remember, is the same as negative 2 over 2, because that would be 1 whole. So really I end up with 5 halves. And then 3 minus 8 would be 5. So again, I'm always using the matrix from the step before. And now again I'm going to have a new row 2. And so row 1 is going to be exactly as it was before. My new row 2 is found by taking 2/5 times the row 2 from here. So if you're good at mental math, just multiply everything by 2/5. If you're not, again, you can show any work that you need off to the side. So 2/5 times 0 is 0. 2/5 times 5 halves, that's the whole point. That's why we came up with that, which we'll talk about more in the next video, is 1. And then 2/5 times 5, which is my last guy, 2/5 times 5 over 1 would give me, oops, I'm sorry, this should be negative 5. Somebody correct me, because I took 3 minus 8, so it's negative 5. So 2/5 times negative 5 would be negative 2. And my last row, if you'll notice, row 1 is the only one changing, so row 2 is 0, 1, negative 2. The good news there is that means y is negative 2. Then I'm going to take my last one, and this one's going to be the hardest one. I'm going to take 3 halves of row 2, negative 3 halves of row 2. I think I've messed up my pen here. Give me just a minute. So I'm taking this row 2, and I'm going to take it times negative 3 halves. So negative 3 halves times 0, negative 3 halves times 1, and negative 3 halves times negative 2. Again, if you're good at mental math, just do it all in your head. I want to show more work for those people who aren't good at mental math and want to write it out. So I'm taking negative 3 halves row 2 plus row 1. So I'm going to then, once I find that answer, I'm going to add 1, 3 halves, and 3 to it. So let's find these answers. Negative 3 halves times 0 is 0, which means my answer is 1. Negative 3 halves times 1 is negative 3 halves, plus positive 3 halves is 0. And negative 3 halves times negative 2 is positive 3, because the 2's would cancel, the negatives would make them both positive. 3 plus 3 is 6. So this guy is a 6. That was a bad 6. This guy is a 6, which means that's my answer. So my final solution would be 6, negative 2. So I want to take a look now at the same thing in reverse. And again, in the next video, we're going to pull it together to talk about how we come up with the row operations, how we determine which one is best. But this time we're just practicing row operations. So I want to know from where I started, so here's my original matrix, and I want to know what is the row operation that led me to my next matrix. So I just wrote these going down like that. So let's take a look. What happened from here to here? Well, row 1 stayed exactly the same, but it looks like row 2, I divided everything by 9. And actually by negative 9. So how would I write that? That I took negative 1/9 of row 2 to be my new row 2. Because that's essentially what I did, is I divided by a -9 to get that 1 in that first position. In my second one, it looks like my row 2 remained exactly the same, but row 1, something happened to it. So let's see what happened. It looks like I divided everything by 4, because 4 divided by 4 is 1, -3 divided by 4 is -3/4, etc. So I'm going to take 1/4 of row 1 to be my new row 1. Now what? It looks like I ended up with a 0 here. So row 2 is the one that's changing. And how did row 2 change? It looks like I took row 1 minus row 2. 1 minus 1 gave me 0. -3/4 minus -2 would have given me +5/4. 2 minus -3 would have given me +5. So row 1 minus row 2 was my new row 2. Okay, so now let's take a look at from here to here what happened. My row 1 stayed exactly the same. Row 2, that 5/4 is gone. So how did I get rid of 5/4? So I either had to multiply the top row by something and then add it, or maybe just multiply or divide the bottom row. And it looks like I multiplied by 4/5, because if I multiplied by 4/5, I would have ended up with 1 here and 4 here. So 4/5 of row 2 was my new row 2. Keep in mind what I was trying to end up at, just like on our last example, was this, so I could know what x and y is. The last thing I would have had to do, it looks like, is to notice the bottom row stayed the same. So this guy stayed exactly the same. The top row then didn't, and it looks like what I did is I took 3/4 times row 2 and I added it to row 1. So let's just see if that's what I did. If I took 0 times 3/4 and added it to 1, I would still get 1. If I took 1 times 3/4, that would be 3/4. If I added it to -3/4, I get 0. And if I took 4 times 3/4, I ended up with 3. I added that to 2 to get 5. So I took 3/4 times row 2 plus row 1 to get my new row 1. Now again, what's the purpose of doing that? The purpose of doing that is because I want to end up here, where I have 1, 0, 0, 1, which means x equals 5, y equals 4, and I found my solution, 5, 4. Now, you might not love matrices, some people don't, but really think about that what you're doing is essentially what you would do if you were doing the elimination method like we did last week, because that's really what we're doing, is we're turning them into the same coefficient, opposite signs. We can add them together. We're just showing work a little bit differently.